Hi everybody, and welcome to exercise 5C. Okay, and we're continuing with series and trying to determine whether the series they're giving us converge or diverge. Okay, so let's take a look at C here together. So we're given the sum n equals 1 to infinity of 1 over n e to the n. What test might we try on this series? Okay, well, you can kind of see that the test for divergence isn't going to help us, because if you take the limit as n goes to infinity of this nth term, you're going to go to 0 because that denominator is getting big. Okay, you might notice though, there's something kind of nice in this series that we haven't seen yet. We've got an e to the n. E is a constant being raised to a variable power, and that's an indication that the ratio test might work for us when you see something like that. All right, so let's give the ratio test a try here. All right, so the way that the ratio test works is to think of the nth term in our series of an, and we're going to take the limit as n goes to infinity of an plus 1. Okay, so that's going to be, well, let's write it out first. Okay, so we're going to start from there. And if we actually write out what an plus 1 is, remember, that's just the nth term in our series with n plus 1s substituted in for all of the n's. Okay, so there's an plus 1. We're going to divide by a to the n, which means multiplying by the reciprocal, okay, which would look like that. Okay, and you might notice here that everything that we're taking the limit of is positive, so we don't really need to write these absolute values. Okay, so we can drop those. And let's go ahead and multiply the fractions together. So if we multiply the numerators, we're just going to get n e to the n in the top, and in the bottom, n plus 1 e to the n plus 1. And then the question is, can we do any cancellation here? Okay, well, notice that e to the n and e to the n plus 1, we can cancel those. We've got one extra power of e in the bottom. Okay, so after we do that cancellation, we've got an e in the bottom. And we can rewrite the whole thing then as n over n plus 1 times e. Okay, and since that e in the denominator is a constant, how about if we go ahead and pull that out? What's left is just the limit as n goes to infinity of n over n plus 1. Okay, well, that limit that we've got has the form of infinity over infinity, so we can use L'Hopital's rule on this. And if we take the derivative of the top and the bottom, we're just going to get 1 in both cases. So we've reduced this all the way down to a constant, 1 over e. That's the value that we're calling r when we do this test. Okay, so the question is, what does that mean? Well, if you look back at the ratio test tells us that we get convergence if the value of r is less than 1, and 1 over e, that's certainly a number that's less than 1. All right, so looks like this is a convergent series. All that's left to do is just to write a short proof of this. Okay, and the idea is that since the r that we got is less than 1, we know that the given series converges. Okay, and looks like we're done with part C here. So let's scroll up and see if we can do part D together. All right, so in D, we're looking at a series sum from 1 to infinity of negative 1 to the n over the square root of 2n cubed. I'm hoping that you might recognize this as a special kind of a series. That minus 1 to the n that we see in the numerator has the effect of causing the signs of our terms to alternate. Okay, we're going to start with a minus, then a plus, then a minus, then a plus, and so on. This is an alternating series that we're looking at. Okay, and it's customary to rewrite this, okay, by kind of taking that minus 1 to the n, the part that's causing our terms to alternate sign, and just factoring that to the side. And we had a name for this leftover piece, we called it Bn. Okay, and since this is an alternating series, it's natural to try the alternating series test when we do this. Okay, and that involved basically checking two things. All right, so I think this one's maybe simple enough that we can start our proof without doing scratch work. Okay, so the first thing we want to convince ourselves of, or to check, is what happens if we take the limit as n goes to infinity of our Bn. Okay, well, can you see what's going to happen there? We've got a 1 in the numerator, and the denominator's going off to infinity, and so that limit is 0. That's one of the two things that we need to happen when we use the alternating series test, so we're good so far. And the other thing that we wanted to check is that the Bn terms get smaller. Okay, in other words, that if you have one term and the next term, you always want the next term to be smaller than the term before it. Okay, so what we'd like to be able to say is this, that Bn plus 1, okay, which would look like that, we'd like to be able to say that that's less than Bn. Okay, and what do you think? Do you believe that inequality that we just wrote down? That really has to be true because we've got a bigger denominator over here on the left than we do over here on the right. Okay, so that's also a true statement. And so we've just confirmed that Bn plus 1 is less than or equal to Bn. That was the second condition that needs to be true in the alternating series test. Okay, and so since those two conditions are true, we know that the given series converges. By the alternating series test. That's what we used. Okay, and I believe we have completed part D.